On March 11, 2011, Japan received a brutal lesson from nature. A magnitude 9.0 earthquake pushed walls of water up to 15 meters high onto the coast of Tohoku. At that time, Japan believed they were safe with their old seawalls, which were only 6 meters high. But against the power of the ocean, that defense system crumbled like toys. The water overflowed the top, eroded the foundations, and washed everything away. More than 20,000 people lost their lives. This disaster posed a vital question. How do we protect people when nature gets angry again? Japan's answer is the craziest project of the 21st century. A reinforced concrete wall, 400 kilometers long, as tall as a 5-story building, running along the Pacific coast. A great wall worth $12 billion. So how did the Japanese make such an impossible project a reality? What technologies did they use to build this steel fortress in the middle of nature's harshest conditions? Let's decode the entire construction process of this massive project right now. And before we start, don't forget to hit the like and subscribe button to explore the world's next mega projects with us. To build a 400-kilometer wall across complex terrain, Japanese engineers divided this massive project into 2 main fronts. One is the onshore wall, where water can be blocked for construction, and 2 is the offshore breakwater in deep water. The first challenge appeared immediately. Engineers faced an engineering paradox. How do you place a concrete block weighing millions of tons onto a coast made of sinking sand and soft mud without it collapsing? Most of Japan's coastline has extremely weak geology. When an earthquake happens, this soil suffers from a phenomenon called soil liquefaction. Solid ground suddenly turns into a liquid like soup, causing structures to sink, tilt, or flip over. To solve this, they use the most advanced technology, deep cement mixing, DCM. Instead of digging up the soil, massive drills plunge deep into the ground. The drill tip pumps high-pressure cement slurry while the blades mix it evenly with the soil on the spot. After hardening, this mixture turns into thousands of super-hard soil cement pillars, packed tightly under the foundation. This system turns sinking sand into a solid concrete platform, completely eliminating the risk of liquefaction. With the foundation stabilized, the onshore wall construction begins. First, since the wall sits right at the water's edge where tides and groundwater are constant threats, engineers must create a dry work zone. Excavators drive rows of steel sheet piles into the ground to form a watertight enclosure. Then, high-power pumps suck the water out, revealing a completely dry foundation pit for workers to operate. After dredging the soft mud, they lay a geotextile fabric and a thick layer of gravel for drainage. On top of this bedding, workers pour a wide, thick, reinforced concrete slab. This acts as the solid footing to support the immense weight of the wall. Next, the main body rises using the cast-in-place method. Workers erect a dense steel skeleton, then assemble massive steel forms standing dozens of meters high. Fresh concrete is pumped into the molds in segments of about 20 meters. A crucial detail is the expansion joint. Between segments, they must leave a gap filled with elastic material. This allows the concrete to expand and contract with the seasons without cracking. And it doesn't stop there. In coastal sections subject to the most intense abrasion, engineers reinforce the wall with an extra front armor. They install high-density precast concrete panels directly onto the seaward face. This hard shell takes the brunt of the impact and erosion, acting as a sacrificial skin to ensure the steel core inside the main wall remains absolutely safe. Finally, behind the wall, they place a filter layer of rocks and an underground drainage pipe system before backfilling with soil. This ensures that when heavy rain or ocean water spills over, the water drains away immediately, eliminating destructive pressure from inside. But in deep bay waters, we cannot drain the ocean. Here, engineers use a massive modular method called caissons. The process starts with barges dropping millions of tons of rocks onto the seabed, creating a flat rubble mound as a base. On land, they precast gigantic hollow concrete boxes as big as apartment buildings. Tugboats tow them out to sea and sink them precisely onto the prepared rock mound. To keep these boxes standing against rough waves, they pump sand or rocks inside, turning them into immovable blocks weighing thousands of tons. A brilliant design detail lies in the shape of the wall. If you look closely at the cross-section, the wall is not vertical. The side facing the sea is designed with a sloped face at a precise angle. This is to fight against the uplift force. When a tsunami hits a vertical wall, water pressure tends to go underneath and lift the wall up, causing it to flip over. But with the slope design, the water is forced to slide upwards. At this moment, the weight of the water itself pushes down on the slope, helping to pin the wall tighter into the ground. Japanese engineers use the power of the wave itself to hold the structure. Combined with that, they drop thousands of tetrapods, four-legged concrete blocks, in front. This armor layer acts as a shock absorber, breaking the wave's energy before it touches the main wall. The final challenge was traffic. We cannot block busy seaports. The solution was mechanical masterpieces, automatic tsunami gates. At large ports, they use the flap gate. A thick steel plate weighing hundreds of tons hangs suspended between two concrete towers. When the tsunami warning triggers, latches open. Gravity pulls the steel door down, sealing the port entrance in just minutes. Even more impressive is the technology for narrow spaces, the vertical gate. Normally, the gate lies hidden completely underground. When needed, a high-power hydraulic cylinder system pushes the entire steel wall straight up from the ground. This system requires absolute mechanical precision, so it doesn't get stuck by rust or mud during decades of waiting. After nearly a decade of continuous construction, with over 30,000 workers, this massive wall is complete. In terms of effectiveness, supercomputer simulations show, even if the wall cannot stop 100% of the water in a mega tsunami, it will reduce the flow power by 50%. Most importantly, it delays the time water floods inland. In a disaster, those few minutes of delay are the line between life and death. This 400-kilometer seawall is proof of humanity's relentless effort. It is a combination of advanced foundation treatment, strict construction processes, and mechanical precision. Japan accepted the cost of $12 billion to send a message. We may not control nature, but we will do everything to protect life against its rage.